probably understand because Cheryl taught us everything we need to know almost. But let's go into the details. So we have a group G, which is a permutation group. So it can be thought of as a subgroup of the symmetric group on omega. And this group is transitive and it's also finite. So I care about the finite groups. And then G, we can define a component-wise action of G on omega cross omega as well. And the orbits of G on this omega cross omega are called the orbitals. And there are two types. One of them, there is only one, and it's called the diagonal orbital, where the two things in the pair are equal to each other. And there's only one because of the transitive action. And every other orbital, where the two things are not equal to each other, are called non-diagonal orbitals. And we can define an orbital graph associated to every non-diagonal orbital, where the vertices of this graph are just the things in omega, and there is an edge between A and B, if and only if that pair was in our chosen orbital. And we want these to be non-directed, so we don't care about their order in the pair.
I'm sorry.
Oh, my Siri is also listening. Anyway, so now there is a theorem by Higman, which says that for a group G, all the non-diagonal orbitals are connected if and only if the action of G on omega is not only transitive but primitive, which we learned from Cheryl what it means, so it doesn't fix any non-trivial partition of omega. And so we can now define the orbital diameter of primitive permutation groups. And it is just the supremum of the diameters of all the orbital graphs that it has. And we'll denote it by orbit diameter. Okay, so example 1. Our group G is 2 transitive on omega. What is the orbital diameter?
This is a quiz, right?
Yeah. Okay, so his transitive means that it has only one orbital because it's transitive on the pairs. So what is the orbital diameter? Is 1. Because then there is only one unique non-diagonal orbital graph, and then that is the complete graph. Okay, example 2. We take G to be the symmetric group on 5 points, and then we take our omega to be the size 2 subset of the set 1 to 5. Then this has 3 orbitals. One of them is the diagonal one. The other one is gamma 1, where the 2 pairs are disjoint. And then the other one is where the 2 pairs have an intersection of size 1. And then for this one, the orbital graph is the Peterson graph. This has diameter 2. And then the complement of the Peterson graph is the orbital graph for gamma 2. And that has also diameter 2. So the orbital diameter of this is 2. But we can think about this in a different way, because it's not so difficult to see that the orbital diameter is bounded above by the rank of G, which is the number of orbitals, which is the same as the number of orbits of the point stabilizer, minus 1. And then that number is 2 in this example. Okay, so the first, I guess one of the first people that got interested in the orbital diameter of the primitive permutation groups were my supervisor Martin Liebeck and McPherson and Tent. And they wrote a long paper in 2009 where they classified the infinite families of groups such that they are bounded, so that there is a natural number, so that every group in this family have their orbital diameter bounded by this specific number. And their research was motivated by model theory, and a lot of their proofs were also model theoretical. So this T is not an explicit bound, they just prove the existence. So we have 2 goals. Goal 1 is to find explicit bounds on the orbital diameter, and the second goal is, because we're finite group theorists, to classify the groups with small orbital diameters. So as we know, the primitive permutation groups are put into families by the Scott theorem, and today I'll be talking about two families and try to fulfill these goals. So the first type that I'm going to talk about is the groups of diagonal type. So we start with a simple group T, and we take T to the K to be just a direct product of K copies of this group T. And we define the diagonal subgroup to just be K tuples of the same thing in the simple group, so it's isomorphic to this T. And then omega will be just the right cosets of D and T to the K. And this Cheryl called the T to the K minus 1 because this is just the same thing because of how the right cosets are. And then we define a group of diagonal type to be this G that contains this T to the K and is in the normalizer of T to the K in the symmetry group of omega, which turns out to be isomorphic to T to the K dot out T cross SK. And then we know how this T to the K bit will act on the right cosets, but the automorphisms will just act on the coset representatives component-wise, and then the symmetry group is just gonna permute the coset representatives around. Okay, so it turns out that between the orbital diameter of groups of diagonal type, there is a connection to the conjugacy width of the simple group that we started with, which is a lower bound of the covering number of the symmetric group. And the conjugacy width is the smallest such number, so that if you take any conjugacy class and its inverse, so T and every conjugate of T and T inverse, then T is equal to 1 union the conjugacy class to the conjugacy class C of T. And then the covering number, we just have that C to the covering number is T. So obviously that's an upper bound. And that's something that people thought about more than the conjugacy width before. So here is our answer to goal 1, to find explicit bounds. And today I'm only gonna tell you the answer to some simple diagonal groups, but if you're interested in others, you can ask me. So we take X to be a primitive subgroup of SK, and then we can show that the orbital diameter of T to the Kx is bounded below by 1/2 K minus 1 C of T. And we can also show that if this X is actually SK, then the orbital diameter is bounded above by 24 K minus 1 squared C squared of T, so there should be another 2, sorry. And then we can also prove that the orbital diameter of the simplest diagonal group ever, T squared, is exactly the conjugacy width. So for a lot of these, we can exactly tell how much it is, because there is a lot that we now know about the conjugacy width. So we have this theorem that if T is a simple group of Lie type, and R is the Lie rank of this group, then Ehlers, Gordev, and Herzog showed that the covering number of T is bounded above by dr for some d in the natural numbers. And I showed that the conjugacy width is bounded below by the rank -3. And in fact, for most of the groups, it's actually usually even the rank that is a lower bound, but R-3 just works for all of them. And so now to answer to fulfill the goal 2, to give a classification of groups with small orbital diameter, then we just give this little classification, and Arachillag and Moran showed that the only group with covering number 2 is the Janko group 1, and it's in fact also true for the conjugacy width. And then I did a similar classification for the conjugacy width. So the conjugacy width is 3 if and only if the covering number is also 3, and then T is one of 6 infinite families, for example, PSL2Q, or 13 sporadic groups, for example, the monster, or A7. So putting these together, we can fulfill goal 2 to have a classification. So it turns out that if we again stick to our example of t to the kx, then the orbital diameter of G is 2, if and only if k is 2 and t is J1. And the orbital diameter is 3, if and only if k is 2 and the conjugacy width is 3. So t is in our list from the previous slide. And the orbital diameter is 4, then k is 3 and t is J1, and we don't know what the orbital diameter is in this case, but we suspect it's not 4, but we don't know. And or k is 3 and c of t is 4, in which case we do know that the orbital diameter is indeed 4. Okay, so now moving on to the groups of affine type. As you recall, Cheryl already told us when these are primitive. So G is VG0, where G0 is the point stabilizer of 0. And then V is a vector space, which will be omega, the set that we're going to be acting on. And then V will just act on itself by translations. And then the point stabilizer of 0 is a subgroup of GLV, and it acts irreducibly on the vector space. So the orbitals are always of the form 0a to the g, when a is a vector. And then it's quite natural to see that the diameter is of an orbital graph is the smallest k, such that we can express every vector in the vector space as a sum of at most k things in the orbit of a to the g0, or the negatives of these, because again we're looking at an undirected graph. So since this g0 is a subgroup of GLV, we can, and it's irreducible, it's quite natural to think about Aschbacher's theorem, and then that just gives us the possibilities for this. So I've been looking at one Aschbacher class, which is the almost quasi-simple cases. So here is the answer to the explicit bounds case. So again, G is an affine primitive group, G0 almost quasi-simple, and V is an irreducible module in characteristic P. So if G0 is of type alternating group, then the orbital diameter is at least L-5 over 2 log 2L. If it is a group of Lie type in cross-characteristic, then the orbital diameter is at least R to the L-1 over L plus 1 cubed log 2R. And if we're in defining characteristic, then the orbital diameter is at least the floor of L half, or V is the natural module of a classical group, in which case the orbital diameter is always at most 2. So using this, we can so the answer to goal 2 is in progress, but I will show you the answer for the defining characteristic untwisted groups of Lie type case, because that one is complete already. So we have that the orbital diameter is at most 2, if and only if the group and the vector space are one of the following. So it's either G2R, V6R, and oh, this should be an R, sorry, and also this. Anyway, and R is even, in which case this has rank 2, so as we learned before, it has diameter 1. The next one is G2R and V7 of R. This has rank 4, so this is not trivial, because our bounds would, from the example 2, would only tell us that the orbital diameter is at most 3, but we can actually show that it's 2. Then the next couple of examples, A4R, V10R, it has rank 3, so it's easy. D5R, V16 of R, also rank 3. V3R and V8R, it's also rank 3. And then V4R, V16 of R, it's also rank 4, but it has orbital diameter 2 as well, somehow. And then if it's classical and it's a natural module, then the orbital diameter is also very low. Okay, so I think that's all I wanted to say.